And welcome back. As we continue our cosmic journey by moving through our solar system, let's go ahead and take a look at the geology of Mars. So when we start looking at Mars in comparison to our other neighbor Venus, we might find that Mars is a more hospitable world. Mars is more interesting for us to study because it's more hospitable, and we're not simply just talking about where this planet might be located, but also what is on it. So even from the distance of Earth, we can see surface features on Mars and follow the seasonal changes in its polar caps. Remember, on Venus, we don't get to see a lot of these features because the atmosphere is so thick that we have to use radar to actually see the surface. And although the surface today is dry and cold, there is evidence collected by spacecraft that has suggested Mars once might have had blue skies and even lakes of liquid water. So we can use this to kind of help address our quest for life. There has been a long and detailed quest to learn about the geology of Mars through numerous missions that have shed light onto our neighboring planet. We actually first started sending probes and landers to explore Mars in the 1970s. Now, the initial results from those probes revealed what appeared to be at first a relatively dead planet, which of course was the dismay of many people hoping to find life here on Mars to say, what can we learn about it? However, the focus on the possibility of life returned with the 2020 launch of the large rover Perseverance. And what it did is it landed in a former lakebed to drill into ancient sedimentary rocks and collect small samples to be returned to Earth for laboratory study. Now, those samples, as of this recording, have not yet been returned to Earth, so we don't know the full analysis of them. However, we, of course, have now collected those so that way we can do some initial data and analysis. And we don't have to rely on simply sending probes out to collect information about Mars. We can actually look to Martian meteors for some information. So, you might wonder, how would rocks have escaped from Mars? Because, well, if they're a Martian meteor, that means that somehow Mars must have ejected them. Well, many impacts from Mars occurred on that red planet very early on in its history. As you can see here, this rock is a rock that came from the Martian surface, and we can see that Mars itself has very many heavy impact craters. And those impact craters, when they hit, remember, there's going to be fragments blasted out from those large impacts, and a lot of times some of those impacts are going to have projectiles that can actually escape from Mars. And remember, the thing about Mars is that its surface gravity is only 38% of Earth's, so they don't need as much momentum to actually escape the planet's pull. A very small fraction of these fragments actually will then collide with Earth, and some of them can even survive their passage through our atmosphere, just like other meteorites can. So, looking at those meteorites, the thing you have to understand is we can start analyzing them. And we find that a lot of them are volcanic basalts that are about 1.3 billion years old. We know from the details of their composition that, of course, that these are not from Earth, or the Moon, or Venus, as it would be very difficult for a ejecta to escape through Venus's thick atmosphere, for example. And we know they're not from Earth because we know the composition of what we find on Earth, and we know that the Moon has a similar composition. So the only reasonable origin must be Mars. And if we look at those raw meteors that we have, this is where the Tharsis volcanoes were active during that time period, about 1.3 billion years ago. So it matches up geologically. Now, the Martian origin of these meteorites was confirmed by the analysis also of tiny gas bubbles that was trapped inside of them. Now, these bubbles of gas that were trapped match the atmospheric properties that we know about Mars. And it appears that some atmospheric gas was actually trapped in the rock by the shock of the impact when it was ejected from Mars. One of the most exciting results, though, of the analysis of these samples has been the discovery of two things. We have water that we have there, so we are able to confirm the presence of water on Mars, and also organic compounds in them. And organic compounds are very important because a lot of life today is very carbon-based, and so we can use that as a piece to say, could there have been life? So let's look more at some global properties of Mars, though. Mars has a diameter of 6,790 kilometers, which is just over half the diameter of Earth, giving it a total surface area very equal to the continental land of our planet. Now, its overall density of 3.9 grams per centimeter cubed suggests a composition consisting primarily of silicates but with a small metal core. Now, Mars has no global magnetic field, unlike Earth, although there are areas of strong surface magnetization that indicate that hey, there once was a global field billions of years ago. Now, apparently, the red planet has no liquid material in its core today that would be able to conduct electricity. And so we can use this now to shift over to looking at the topology of Mars, what we see on the surface. Approximately half of the planet consists of heavily cratered highland terrain found primarily in the southern hemisphere. The other half, which is mostly north, consists of younger, lightly cratered volcanic plains. And a geological division into older highlands and younger lowland plains seems to be characteristic of all the terrestrial planets except for that of Mercury. Now, lying across the north-south division of Mars is an uplifted continent the size of North America. This is the 10-kilometer high Tharsis Bulge. It's a volcanic region crowned by 4 great volcanoes that rise still higher into the Martian sky, as we can kind of see here in this picture. So, speaking of volcanoes on Mars, the lowland plains of Mars look very much like what we might expect to see from the lunar Maria, and they actually have about the same density of impact craters. Now, like the lunar Maria, they probably formed between 3 and 4 billion years ago when Mars experienced extensive volcanic activity, producing similar balsa lavas. Now, the largest volcanic mountains of Mars are found in the Tharsis area, although there are small volcanoes that dot much of Mars' surface. Now, images taken from orbit have allowed scientists to search for impact craters on the slopes of these volcanoes in order to estimate their age. Many of the volcanoes show a fair number of such craters, suggesting that a lot of these volcanoes cease activity a billion years or more. Now, one of the most famous volcanoes on Mars is Olympus Mons. This is kind of the most dramatic volcano that we know. Olympus Mons, with a diameter larger than 500 kilometers and a summit that towers more than 20 kilometers above the surrounding plains. This is 3 times higher than the tallest mountain that we have here on Earth. Now, the volume of this immense volcano is nearly 100 times greater than that of Mauna Loa in Hawaii. Now, placed on Earth's surface, Olympus would be huge. All right, it would actually cover the entire state of Missouri. Olympus Mons has actually very few impact craters, though, which suggests that this volcano is actually still pretty young, or might even still be geologically active. Now, volcanoes, of course, aren't the only defining feature. We also have cracks and canyons that line the surface. The Tharsis Bulge has the surface bulged upward, forced by great pressures from below, resulting in extensive tectonic cracking of the crust. Among the most spectacular tectonic features on Mars are the canyons that we call the Valles Marineris. They extend for about 5,000 kilometers, or nearly a quarter of the way around Mars. Now, if the valleys were on Earth, this canyon system would actually stretch all the way from Los Angeles to Washington, D.C. Now, the main canyon is about 7 kilometers deep and up to 100 kilometers wide, large enough for the Grand Canyon of the Colorado River to actually fit comfortably into one of its side canyons. So it's pretty large in comparison to the canyons that we have here on Earth. Now, there is some misleading terminology that when we look at these canyons that we might assume. The term canyon is not necessarily correct because Valles Marineris canyons have no outlets. And they weren't cut by running water, but instead were tectonic cracks produced by crustal tensions. However, water has played a later role in the shaping of these canyons, primarily by seeping from deep springs and undercutting the cliffs. This undercutting led to landslides that gradually widened the original cracks into the great valleys that we actually see today. Now, today, the canyons, of course, can still shape and change, but the primary form is coming from wind rather than water.